So this is going to be the decay part. Come on.
Is this the same?
Yeah, I'm just figuring this out.
Okay.
What if I actually send them to you with HB? You already know
So being
those.
reset by yourself, you wouldn't talk as much.
Well, I was just after
Is this exponential?
This is exponential decay. It's the second part of this. It's mainly coming out of 8.2. Like I said yesterday, a lot of the stuff that we're working on is a mixture of the first couple of sections. So yesterday when we were dealing with exponential growth, our growth models had b values that were always between greater than 1. All right? Our growth models all had b values that were greater than 1. And our graphs, remember, were either increasing going from left to right or decreasing going from left to right. Remember that? Now, decay problems, exponential decay, have a very subtle difference. What I want you to do is we're going to plot a parent function of decay. So give me some b value that's between 0 and 1.
3/4. 0.5. Wait, 0. Wait,
I
no.
don't know.
It's not a trick question.
I said 3/4.
I know you did.
Continued from yesterday?
So what I want to do here is we're going to pick this parent function, and we're going to say that we'll do y equals 3/4 to the x. If I say it's y equals 3/4 to the x, what's my a value?
1.
It's my 1. So where's my y-intercept?
1.
1. So let's go to our calculator, and let's put this in. Now, with some of these fraction ones, do you have to use the fraction bar to put in the fraction, or could you type 0.75 if you really want to? It's fine. Now, the only time I would say don't use the decimal equivalent if it's like a third, sixth, something that's not a repeating decimal. Yeah. So it's just quicker to sometimes type 0.75 to the x. And let's just look at this graph. What's different with this graph versus what we did yesterday?
Oh, go the other way.
It's going the other way. And that's really all it is.
Really?
Yep. The difference between the growth and decay models here is that in exponential growth, your b values were greater than 1. In exponential decay, your b values are less than 1, but greater than 0.
So can b's never be less than 0?
Correct.
Wait, so it's going to be like a fraction all the time?
Well, remember we had fractions here yesterday. We had 3 halves.
Well, yeah, but now b is always going to be
Yeah.
decay.
Correct.
That's okay.
All right. So now that means your graphs are either going to go down and right,
Or down and
down and left, I should say. Down and left or up and left, is the way I should say. So your 2 graphs will look like that.
or not.
Okay? That's the difference between growth and decay. The actual model itself, the equation for them, is the same. For growth and decay problems, we still are going to use y equals a times b to the x minus h plus k, where it's growth if b is greater than 1, it's decay if b is less than 1 but bigger than 0. The a value, if you recall, tells you the direction. Yesterday, if it was going from the right or from left to right going up, we knew a value was positive. If it was going from left to right and it was moving downward, a was negative. Here, if it's going from right to left, moving up, a is positive. Going from right to left, downward, it's negative. The a values in these things tell you what direction the curves are going to go. Yeah?
So if it ends up going down, basically, it's negative.
Correct.
Okay.
Well, remember, this is still moving down.
Yeah, this is easily going to get confusing.
Just remember,
that.
Yeah. So you just have, it's very easy to just look at the graphs here. The other thing I want you guys to notice, the domain for these things has been all real.
Yes.
Okay? The range, if you've noticed, it's been bounded by the k value. You picked up on that?
Yes.
Yeah.
No.
Your range is dependent on on k. And here's what happens. Remember, if your a value was positive, it was moving upward, correct? So all the range was always the y values that were greater than k. If the a value was negative, it was the range was all the k values that were less than k. So here's how this works. Your range is y greater than k if a is positive, and then it's the other way. Yeah. It works for both of them, actually. It's for both growth or decay. Your range will be bounded by that, and it works every time. What's that? Yeah, you do a lot of, there's exponential, there's decay, radioactive decay and all that kind of stuff, it's all in there. Decay, you think you start with some initial amount and you're losing it over time? Start with the initial amount and it's growing over time. These just means your leading term was negative. In the scientific world, it's generally not looking at these two. Real world applications, usually a value is positive. Don't get me wrong, there might be a model out there somewhere that has a negative value. I don't know off the top of my head. Okay. So what's nice then is that you're going to be able to look at an equation and you can tell me domain and range without doing anything.
All real.
Domain,
Domain is all real, and y is, no, y is greater than 6. No, it is less than 6.
perfect. Just by looking at that, knowing that the a value is negative, you see how easy that is? And that's the idea of understanding what all of these values mean within the generic forms of these equations. So when we were talking about reviewing for the final last semester, when I said it's not that you had to know how to do the entire problem correctly, could you identify parts of it to make it easier on yourself?
And discount several.
Exactly. And that's the idea of some of these types of things. You know where it's going to look like, you know that the graph's going to go in a certain direction, just by the rules. If it doesn't show up like that, you've done something wrong. So let's do a decay problem. Let's do this one. What was that? Okay. So we have y equals 5 times quantity 1/2 to the x plus 2. Is this going to be growth or decay?
Decay.
Oh wait, it's not B, so it's decay.
It's decay. I know.
Wait.
It's going to be decay because what's your b value?
1/2.
1/2.
Oh, so it's less than, okay. Wait, so can it be, everything between 0 less than 0 for anything?
Great question. Great question. Can the b value be less than 0 for anything? What's your b value?
3. Negative.
What's your a value?
Negative 1.
Oh.
Okay.
Great question.
So the answer
Great
is
question.
no.
Oh, wait, unless you
no.
put parentheses
Yeah.
around it, because depending on what the x is.
Wait, what? And then, yeah,
What's the negative times the negative then?
Well, no, think, if x was 3, okay, and you just
Did you hear
had.
that? Well, no. Think. Sorry. Okay.
Okay, so if x was 3 and the negative 3 was in parentheses.
All right. So what you're saying?
Okay, so negative in parentheses and the exponent is 3, that would equal 27, right?
No, it'd be negative.
Negative. Okay. I think. Yeah, okay.
What? What if it was just?
Oh, the exponent is x.
The exponent would have to be x here.
Yeah, alright.
All All right?
What if it was that, and then your A was just 1?
Well, what's happening here is that this won't be exponential because you're grouping it with the negative value. Doesn't work. This has to come out to become the negative A value.
So.
That has to be. B will never be negative, is what I'm getting at. It can't be.
Okay.
All right? You're overthinking
Your
it.
loopholes don't work.
Yes. These aren't the droids we're looking for. So, what's your A value?
I enjoy this.
H is
0.
K.
2.
All right. Now, we know it's decay. When you go to plot a decay problem, you plot it the exact same way you plotted growth problems. You start with your parent function, 5 times 1/2 to the x. What numbers do you think I'm going to use?
Negative 2.
Okay. Now, this is where some people have been screwed up earlier today when you're dealing with the fractions with negative exponents. So a quick little refresher. We have 5 times the quantity, 1/2 to the negative 2.
So it's 4. That's like, that works out better when it's a half thing.
Will it always be like not super hard fractions, or will
They
it?
normally aren't, and they're not going to give you like 17 over 33.
Okay.
I mean, I might, but both won't.
If you do that, do we get our calculators?
No,
Okay.
Wait, hold on.
I won't do that.
Wait, what's that?
Yes, ma'am.
Wait, why is that?
1/2 of the negative 2 is 4.
Correct. Now, remember, what's happening here is you're using your properties of exponents. The property of exponent tells you when you have a fraction raised to an exponent, both the numerator and denominator both get that exponent. Since this one's negative, you might as well just flip it right away.
2 over 1 squared, and 2 squared is 4.
So that's why we're getting 4 times 5,
20.
20.
2 times 5 is 10.
Can you go over that for
5.
Yep.
5 times 5.
What's happening, remember, what's happening when you have a property of exponents is that you have a, b to the negative n. What you would do is you have a to the negative n, b to the negative n, which is b to the n. A. So what I did is I just flipped it first and then squared it.
Okay.
Does that make sense?
Yeah. In this way.
So now you've got your ordered pairs for your parent function. Negative 2 and 20.
Can I just go by like?
Up there, negative 2 and 20. Negative 1 and 10. 0 and 5.
Did he actually put?
1 and 5 halves. And 1 and 5, 2 and 5 fourths.
I wonder how it sounds on the video.
When you do that, where is your horizontal asymptote for the parent function?
0.
Good job, Mike.
So I know it's going to go, it's got to go that way.
But you have to do it out of line.
It's okay. We'll get over it, right?
I won't.
Just
you should.
think of it as an imaginary line.
Um,
Now, to each of these points, what do we have to do?
Add shift now.
Shift or up to.
Everything's got to get shifted up too, correct?
Yeah.
All right.
You better draw that dot up there.
I just shifted everything up too.
Yeah. Wait, I will do what you did.
You can just do, how can you not tell?
It's moved the graph.
Wait, so do we have the asymptote?
You have to move.
Now the asymptote moves as well. That's the one of the reasons why I did that is just to show you that your asymptote still moves. The asymptote also has to get shifted upward. So now your official asymptote is at y equals 2. Okay. Now, Kristen, you were talking earlier about how you're going to get the y-intercept. This one works out cleanly because it lands on a spot.
Yeah, I get it.
I'll ask you guys for intercepts that wind up clean if you don't have a calculator. If you have a calculator, you can figure it out. All right? Does that make sense, guys?
Yeah.
Y-intercept for 7.
Yeah. You put 0 in for x for the shift and you'll be all right.
Y-intercept for 7?
Y-intercept in this case would be at 7, correct. Y-intercept would be at 7. This just needs to be turned into a solid line. And remember, when you are shifting these, when we did this before, one of the nice tricks that we did is that we wrote them out as x plus 0 and y plus 2 for your ordered pairs. And you can just add those in on your own and write them out. I'm reminding you of that because that's generally what I ask you to do on any quiz. Fair enough? Not scary, is it? Good. Do this one then, please.
Like how I think it should go.
I'm just kidding. I like math.
What'd you say?
I was like, I'm really.
Do you want me to do it?
Sure.
Okay.
I could.
I didn't actually mark the points yet, but I know how to.
Please do.
I prepped myself up.
Now, try to be nice to her. I know it's a stretch for all of us, but we can do it together.
Why didn't it work? I got it.
Don't harass. That's my job.
Did you guys like give like a rubber gecko to like biology?
I have a rubber duck.
So you don't hear it, like just happen.
Wait, it's you mean Alyssa?
Get out. Anna. I'm really worried about you.
Leopard gecko.
Oh, I thought
she was going, it's 5 years old, why is it dead? Who
What?
wants a leopard gecko when they're 15 years old?
I don't know what. Story time.
Okay, so one,
No, I don't care. It's a math.
so
No, 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 you don't. But anyway.
How does that make you feel?
Wait, am I right so far?
No.
Well, you're on my left, but let's see.
yes, you're right.
You can't
Yeah.
stop.
Okay.
You're
Please
right.
don't
You're right.
cry.
I appreciate it. Don't
We're in a very serious time. You have 15 minutes before you decide on fate.
Yeah, it probably is. Okay, so
Stop.
here's that.
I was trying to Alyssa asked if I was blind and my sister's like,
That's negative 12. Or that's 12.
It's fine.
Wait, it's negative 12.
It's
I did it wrong. I did it.
usually. I think you do. I think you reached this
Try
one.
to come up here and show us what to do.
She's doing fine, guys. Even though we like to harass her.
I'm just taking my time, you know?
Yeah, we know.
Negative 1, negative 6.
You can't stop the beat.
Hungry.
I have thought
Just like
Seriously, if there was an award for the most distracted group of people, you guys all win.
Woo! Won something!
No, just pay
Calling us
attention.
winners.
Oh man, it's like our 5th Friday of the past 2 weeks.
Can I have it, please?
Why?
Okay, I know. That's negative 3/4 today.
Wait, what?
Someone's in
Is that lunch?
Allie's
I have it.
Yeah.
Someone took our team.
My brain hurts.
The freshman boys are trying to take our booth.
All right, do we agree? So far, do we agree?
No.
Yeah.
I completely wholeheartedly agree. I think it's
Yeah.
you're doing a good job.
Yes.
Yes, it's perfect. Now, let me ask you this real fast.
I'm
Where
shifted.
is your parent functions horizontal asymptote?
Is it at y is less than 0?
I'm asking, where is the parent functions horizontal asymptote? Where is the asymptote located? Not
y
range
equals
right
0.
here. Y, perfect.
Y
That's
equals
what-
0.
Yep.
Okay, I'll write it down right here.
You can't stop.
Now, to each of these points, what do you have to do?
Shift us to the left
2 and up 1.
All right, knock yourself out.
Okay.
So also just
I know what you want to do. Move the graph.
Okay, wait. I don't know how to do that.
It's literally
it's
highlighted.
highlighted right now.
Oh, and you unhighlighted.
I also,
She's all right, she's all right.
But she's moving the graph.
Yeah, move the graph. Just move the graph. Let's cheat it a little bit here. Move it to the left.
Wait, I'm going up 1 first.
All right, that's fine.
Up 1,
Move it to the left too.
Move that dot to the left.
1, 2.
Perfect. Now,
wait.
I did it upside, I did it the wrong way. I was
Yep.
also like,
Well, no, because
Why, yeah, you
I
did
instead of
too.
doing
I didn't do that.
positive 12 and a half.
Now,
or something.
Melissa, where is your new horizontal asymptote?
And y equals what?
Very good, very good, very good. Nicely done.
Good job.
All right. Now, again, like I was saying, guys, the big difference between growth and decay
I did a really good job.
weird
You're something else.
is this stuff. When we go back into this, remember your growth graphs do that. If you want to think of it this way in terms of where the graphs are located as far as a parent function is concerned, your growth graphs have positive values for x. Yes, ma'am?
Okay, wait. From that graph that I just did, the domain would be all real, and then the range would be y is less than 1, right?
Very good. Domain, all real, and your range, perfect. And notice how it mirrored the idea of this is negative, and this is your k value, so it's less than. Perfect.
Okay.
I forgot to mention that when you did that, but yeah, very good. So, like I was saying, the idea here is one of the easiest ways to remember growth or decay if you're looking at a graph. A parent function's graph, if it's tailing upward or tailing downward where the x values are positive, it's growth. The x values are negative where it's tailing, it's a decay. Does that make sense?
Yes, sir.
Seriously, you guys are just the
Go back
weirdest.
to my graph. It looked really cool.
We watched the Sarah Palin.
I want you guys to do these this evening.
You do the same problem.
It's the same problem numbers, the next section.
Why? Why?
Why not?
Because I'm gonna get confused.
No, you won't, because you're going to write down the correct problem.
Okay, 477.
Stop! So annoying.
All right? It's
Stop!
477. It's the next section.
Say it one more time. I swear to God. I will leave all your books on top of the locker and throw your lunch away. I will bully you.
All right? These should be relatively easy. When we come in on Monday, we will combine growth and decay word problems, which are actually the easiest problems you will have the entire school year.
Yay!
Seriously, they really are. They really are. It's all about principal, interest, things like that. It's practicality stuff, depreciation, things that you'll actually use in your life.
Wow.
All right?
It's like third grade.
No,